talked about the calculations of trigonometric functions using SOH CAH TOA. That works extremely well for simple triangles. In other words, triangles where you're only dealing with angles or theta up until 90 degrees. If we go back to our first quadrant, remember that we talked about an angle always starting in this position here, where we have 0. As it gets bigger, we might go to 45 degrees and 90 degrees. Up until this point here, any angle that we have, so supposing we choose to stop the clock arm here arbitrarily, we now have our angle theta. We drop from this point here, and bear in mind that that point has a coordinate of x and y. We drop a point, line goes 90 degrees to our x-axis, so we always deal with a 90-degree angle. Remember that, we always have a right triangle. Now at this point here, the opposite to theta is a positive value. The adjacent is a positive value here as measured along the x-axis, and the hypotenuse or the radius of the circle, let's call this r. No big deal. From here we can figure out sine, cosine, and tangent. If we extend the angle now, however, so that it goes around this way, so maybe now the angle is, let's do this in red. Angle goes all the way around to here. Now, we can still follow the same idea. We stop the clock arm here, goes all the way out there. Now radius, of course, is always a positive value because the clock arm has a definite length. We drop our 90-degree line there. Again, we have a new angle of theta, but the theta now sort of stretches around here. We can sort of use the supplementary angle here and use opposite, adjacent, and hypotenuse to use SOH CAH TOA. It gets really weird by the time, say, we stretch the angle around to here. Now we have what's called a reflex angle, and theta goes all the way around to here. Opposite and adjacent become a little bit harder to figure out, similarly when we get to this side here. Now, it becomes a lot easier to handle sine, cosine, and tangent and so on if instead of thinking in terms of opposite side of the triangle, adjacent side, because right around here we're starting to get some angles that are bent way beyond a normal triangle, think of the opposite and adjacent in terms of x and y. Here's what I mean by that. We go back to our original triangles. Let me just get rid of all this other stuff here. We go back to our original triangle here. We have a straightforward coordinate. That point which creates our angle has an x and a y, as I mentioned. Now, if we were to take sine of theta, instead of expressing it as opposite over hypotenuse, SOH CAH TOA, we could express it, well, the opposite side here corresponds to the up and down measurement, which of course is a value of y. So that side here is measured by our y distance. So we could say sine of theta equals y over the hypotenuse, which is r. Similarly, we could say that cosine of theta equals, well, it would be the adjacent side, which is along here, measured by our x value, because that's where it goes as far as that coordinate. X comes up to here. Now notice it's not the radius, it's just that point here, which goes up our 90-degree line to where x is. So that distance, of course, is x, and cosine becomes x over r. Similarly, tangent of theta becomes y over x. This is a lot more useful because we want to resolve some identities where we're now developing bigger equations using sine, cos, and tan. We might, for example, have something that looks like this. Find the value of sine squared theta plus cos squared theta. Most people look at this right now and they wish they were somewhere else. At least you were sitting in math class. This is how we make it easier. So sine squared plus cos squared. Well, we know that sine equals y over r. So let's change that to sub in sine, which of course is y over r. And we squared it. For cos, we take that sub in x over r. So there's our cos. And we square it. And what the heck does this give us? Well, if we expand this out using BEDMAS, we have y squared over r squared, don't forget to square the top and the bottom, plus x squared over r squared equals something. Now, since we have the same common denominator here, we can put it all together so that we have on the top y squared plus x squared over r squared. Now, one of those strategies I talked about in previous videos, and if you're not sure, go back to the previous videos on SOH CAH TOA and whatnot. I will wait for you while you rewind those videos. Actually, I'm just kidding. I'm not going to wait for you. You can always pause. We have x squared plus y squared. Always write down what you know because you might start to see a pattern. This should look suspiciously familiar. Hint, hint, wink, wink. we're always dealing with a right triangle. No matter where we spin the angle, even when we get around past 90 degrees into negative territory for x and y, we're still dealing with a right triangle. And when we have x squared plus y squared, it always equals r squared. So this top part here becomes r squared. So the whole thing now becomes r squared on top over r squared on the bottom, and anything divided by itself is 1, uno. Therefore, this whole equation here, sine squared plus cos squared, equals 1. And you thought this was difficult. If this doesn't make sense, chew on this for a little while. Now, one more thing I'm going to add. When we go around, this still holds true because, supposing we take one of these wacky angles over here. Let me draw this. So now theta is this whole angle around here. It gets confusing because sometimes people think, well, what if we use this triangle here? Which one's opposite, which one's adjacent, which one's theta? You can start to get mucked up pretty fast. However, we don't have to worry about that because here's our y value, but now it's going to negative territory, so it's actually a negative y, that distance there. Here's our r, stays the same because a clock arm always has a positive length. Here's our x distance. Oh look, that's negative as well too. But if we have negative y and we square it, it still just becomes y squared because a negative times a negative is a positive. Similarly, that's a negative x as we head up here. Negative x times negative x is still x squared, becomes positive. This works no matter what angle you have. You can keep spinning around theta as many times as you want, but if you change sine and cos and tan into x, y, and r values, you find it a lot easier to manage. More on this in the next video as we continue to develop it. And remember, if you think this is confusing, I'm only doing these videos because I love you guys.